So if you've watched some of my other videos, the fundamental object in zeta space is the seed. So that is I gamma pi. So let me just go through the individual components of this tuple. All right, so the I is, I'm going to go through this pretty briefly. The I is the four football orbifold sheets. This is the seam graph, and this is the symmetry group. Now this actually, so this is sort of assumes that one is familiar with this framework, I guess, because what we really want is to look at this as a sort of a membrane or a foam, so like sort of like a Klein foam, but there will be differences, namely the symmetry group, the group action will put on this stuff, the seed, or this foam, if you want to call it that. So you should think of the four football sheets as these membranes that are sewn together. And this definition really, it really does resemble a foam because it just kind of constructs it a little bit differently. A Klein foam is constructed. A Klein foam is also a triple. It's a triple. Basically, you glue discs. You're basically gluing discs along a boundary. And just using like a gluing map. That would be phi. Okay. So phi is the gluing map. You're attaching this disc to, say, another disc, maybe. And that's the boundary. All right, so that's all well and good. But, and you're attaching them. Let's say that like in the middle, you're kind of like attaching them to some, I don't know, some graph gamma. All right, so you're attaching them to this graph, this rigid graph, maybe, or it doesn't have to be rigid, just be like I don't know, any some complete graph or whatever. Anyway, you can also have analytic foams, and you can have dianalytic foams, and that's so dianalytic. That's basically just mean, and this is a hallmark of Klein, Klein foams, because we have this dianalytic structure going on. So you think of this, it allows transition maps that are holomorphic and anti-holomorphic. So if you imagine going through this, like you're on this disk and you're going through this boundary, and then you switch and you automatically go to possibly anti-holomorphic transition maps. So the character of that can change across the seam graph. So that is basically super crash course in Klein foams, but it's interesting to see that it carries over quite well to this seed structure. All right, so we'll have these sort of act like the disks. So the disks, these sheets or disks, two-dimensional surfaces. It's the seam graph, and then we have the symmetry group. Now, Klein foams, you might notice that they don't really have this symmetry group. There is a notion of symmetry, but it's mostly an internal symmetry of the foam. So what is this? So what is this pi group doing? Well, it's saying that, and really we should write it. We should write this out a little bit more. So really we should have what we could write this a variety of different ways. It depends on how you want to do it or what's standard, but let's take this, try to match it up this and similar to the Klein foam definition. So I have I gamma. Let's take that gluing map again, okay? And we'll take, we could either write pi or we could write, we could write rho. No, let's write rho for a group action. Because this is just a group, right? We want a group action on this foam. What else? What am I missing? Surfaces, graph, gluing map, seam graph, gluing map, action. Yeah. I mean, we could attach other stuff, right? For example, like, a coloring, maybe. Coloring a extra structure, basically. Enriched structure. So we could do a coloring. We could like color the parts of these. It could be continuous. It could be a discrete set of colors. We could also do a local system. We could do a, what else? We could do holonomy. So I'll just write all for that. There's a lot of things we can do. We don't necessarily need these right now. Just X those out, but we could use them if we want to. Specify extra enriched data on this seed or this foam. Now let's focus on this though. So I'll go like that. So what is this? This is our seed. Okay, so we already went through this. This is the graph. This is the, so let's go through what this is. That's the attaching map. So, and then we'll get to this. So phi is really just phi is really just saying, so if these are I don't know, sheets, so sigma, it's like 4 football sheets, so there's sigma I. So we're gonna do boundary sigma I. These are kind of analogous to those boundary, those disks. And we're going to map that to, I don't know, the graph. Right, so we're gonna map those surfaces to the graph somehow. Now, all right, so that's great. Now let's get a new page going. So now we have, okay, let's write the seed again here. Okay, I gamma. For phi rho. Okay. So we check that off, we check that off, we check that off. now let's take a look at rho here. And recall that rho is the group action. So I say rho, just a group action. So if the group is, say, pi, it could be any sort of, I guess it could be piecewise. It could be, you know, finite. And finite non-piecewise, and it could be, yeah, so basically it's going to be finite. But we're going to take rho to be pi, so pi, and it's going to map to, let's just say the automorphism group, and these are football orbifolds. We're just gonna denote that orbifold, and you know, let's consider piecewise. So p dian, that'd be piecewise dianalytic. All right, so it's dianalytic. We'll just denote it like so. Yeah, so basically rho is a group action, and we have these dianalytic orbifold automorphisms. All right, we'll just write it like that, but essentially it's saying, like, if we do p of, say, let's say pi x for some generator of the group pi. Not to be, this is capital Pi, this is lowercase pi, by the way. Essentially this must, we're associating, say, a generator of this group, so right by, to the automorphism group, to this. And this is quite interesting because mainly because we're in dimension 2, so some special things coincide and coalesce here. It's a generator. Let's say this is, sorry, dimension 2 is special. Dimension 2 is special. Okay, so why is it special? Let's get a new page, actually. So anyway, the point with this was to show that we have a symmetry of the foam, and it's external symmetry, right? So if you think of like a square or something, you know, you rotate, turn it, and it has a symmetry group. This foam, this seed, also has a symmetry group, and a group action, and every element of the group pi, which preserves this. So I'll have some symmetry operations. So generators will correspond to elements, or at least every element here should correspond to every element in the automorphism group there. And we'll see that dimension 2 is special because these are piecewise. So it's this is the piecewise isometry group. I mean, this could be a subgroup. This could be a like faithful subgroup of that. It doesn't have to be all the. It doesn't have to be the full automorphism group. But so if this is like a piecewise isometry group, then what do we get? We're in dimension 2, so we'd get that PIs imply these dianalytic automorphisms. But the converse is not true, because a dianalytic automorphism need not respect lengths. So the converse is not true. Dianalytic automorphisms do not imply piecewise isometries. So this condition in here is much stronger. Much stronger. It allows us to do it opens up a lot of doors for us. So recall that in dimension 2, fixing. So fixing, right? So fixing a Riemannian metric so that's in dimension 2, fixing a Riemannian metric automatically defines a conformal structure. Hence a complex structure. Keep this in mind. This is important. All right, let's move on to what can we do with this, right? What can we do with this? Essentially, we can fix. So remember on these football orbitals. So on these football orbitals, we can define what is called, we can define a spherical metric, which can be easily converted into an action angle metric. And we can define like a metric such as, say sigma. So I'll define sigma I. So sigma I, that's that sheet there. GI. So essentially, what we want to do is define this G. So this is a metric, and we'll do that by doing this. G phi is just 1/phi u d u squared plus phi of u dv squared. Okay, so that's basically an action angle metric, so put that there. Action angle metric. Okay, easy way to see that is that, so this would be the action coordinate, right? This would be the angle coordinate. Okay, you note that theta, just note that v, I guess, and u. So this one would be u. U. Okay. Now we have this metric, and if you want, well, I'm not going to go through the exact warping factor there. This would be a quadratic. But the point is, and this would be the Gaussian curvature of this thing. I mean, this would be constant Gaussian curvature, just for reasons of symmetry, to make this thing symmetrical as possible. This would be what is it? K Gaussian curvature, right? Okay. Oh, sorry, that's -1 here. -1/2. All right, so the Gaussian curvature K will be this. It will be just -1/2 double derivative, right? So let's move on, because this is quite interesting. If we have this metric, so what do? We fixed our Riemannian metric on all of these sheets. Let's fix them on all of these sheets. Same exact metric, okay? So we get a conformal structure, hence a complex structure. Now, that perfectly lines up with what we were talking about a couple minutes ago. So now you should think of, these piecewise isometries as, say, slicing this thing. Say it's tilted just like that. You slice it like this with the plane. So now what do we get? If the plane's right there, tilt the plane here, we are going to get this precise sort of curve, okay? And by the way, this is a piece of the gamma seam graph. So when we slice this and cut it right there, boom, then we're gonna take this top cap. Let's say we're gonna permute it away, or take this bottom cap. We act on it by piecewise isometry. The interesting thing is that these four footballs create this complex, this foam, and that when we slice or do a piecewise dianalytic automorphism, we're really just preserving the dianalytic structure. Now, since we have a stronger condition that the piecewise isometries imply the dianalytic automorphisms, we also have the following fact, is that we now get our hands clasped around the Laplace Beltrami operator. All right, so the Laplace Beltrami operator. Now, why is that, helpful? Well, remember we have football overfold, so we have these locally. If we zoom in, we got these cones, right? So this is our football overfold zoomed way in locally to the cone point. Just call it P. All right. And it has a cone angle. They all have the same cone angle, this simplistic model, but we are going to look at what's going on here. Well, we have the angular, the S1, angular modes, and these are what I said before, but they're local now, so right here, boom, these angular modes. Great. Okay, so we have these radial modes, okay? So angular modes, and radial modes. Now what do we get here? Let's just think of this simplistically. So we're going to get sort of these Bessel function solutions. And what do I mean by that? I'm sort of jumping ahead, but I'll just write it down first. So Bessel functions, angular modes, we're going to get e to the I, 2i pi, whatever, 2i pi, 2i pi, just say v. All right, so 2i pi v, these are our S1 angular modes. And now, why am I, saying these? But why am I saying these? So I'm saying them because because we have a amount of metric, so we have a way to deduce the solutions to the eigenvalue problem, in particular the Helmholtz equation with the Laplace Beltrami. So something like, I don't know, something like that, right? And we got these. Something like this. I forget the Helmholtz equation. Something like this, I think. Yeah. All right, whatever. Right, well, we get something of that nature. So we're going to solve this. Okay, when we solve it, the solutions are, well, the solutions can split into, they decompose into a product of solutions that, since it's a basically a surface of revolution, we get a product split of those solutions into these respective domains. So, I mean, something like this. I mean, this might be, so if we denote the, if we denote the solution, say, as maybe R of M, R of V, okay. R of, I don't know, we'll say R of M maybe, where, I don't know, maybe the entire thing is just that should probably be R, A, B, C, D, E, F, G. It's T. T of V. Okay. So R of M, right? T of V. All right, that's our product split. Let's just MV. Okay, coordinate split there. All right, so that's well and good. And I'm gonna wrap up this video in a moment. It's getting a bit long. So yeah, so let's just see like the forest from the trees here for a second. Is that we solve this local to the, you know, the cone point, any given cone point. It applies to any given cone point of this model because they're all the same. So we just get that, and right, so this gives us a way to understand the local, or at least part of the local spectral information. Local spectral analysis. We get our hands dirty with the local spectral analysis here of this model. So so once we do that, we can sort of, from here, we can do a number of things. We can look at differential equations that propagate these sorts of things, these solutions into the bulk, into the interior. So away from the cone point into the interior of the shape.